recording, I think. All right, so welcome to Teachers as Scholars. So this class is somewhat related to Fibonacci's and stuff like that. I'm just double checking over here to make sure it is being recorded. All right, hopefully it's being recorded. And so I want to start off with just some fun sequences and see if anybody has seen these before and can detect a pattern. Some of them are going to be easier than others. So have people seen this one before, just the sum of the first n integers? Does anybody know the pattern? So off the top of your head, can you give me a formula for if I give you the sum of the first 5, 6, 7, 8? No is okay. And so what you do is you gather data and you start to see, is there a pattern? And for something like this, the pattern's a little bit harder to see than others. So hopefully a slightly easier one might be the sum of the odd numbers. So have people seen this one? So the first one is 1. Let's go around the room. Next one is
4.
4.
9.
9.
15. No, 16.
16.
Am I adding 9?
You're adding 9.
25.
36.
36. So now we have a really good conjecture here that this looks like it's the sum of the squares, right? The previous one, includes the sum of all the integers. That was a little bit harder to do, but we were able to pretty quickly detect a pattern in just the sum of the odds. So, again, I'm going to just pretend Henry's not here, rather than just doing the equipment malfunction. I'm old, I'm over 50, I've done this so many times, I really don't plan classes anymore and just see what happens as I talk to people. And so had no idea what I was going to say, still don't, thinking of it right now on the spot. Maybe, is there a way to use our knowledge of what's going on for the sum of the odds to try to figure out the sum of everything? Because if you look at the evens, well, the evens is just double the sum of everything, but to a smaller number. So maybe there's a way to somehow take the information about the sum of the odds and use that to get everything else. So there are some games that you can play. This is going like the sum of the first n odds is like n squared. Well, if you look at the evens, that should also be something that of size n squared. It should be comparable. So maybe there's a nice formula as well. Maybe there's a quadratic at n for that as well. And so we can talk more about that later if people are interested. Okay, so I want to start off with playing games. And so I'm going to start off with probably one of the most boring games known to humanity, the I Love Rectangles game. So what's nice about this is you can play it with people all the way down to kindergarten, and I have done that. The only acceptable shape in the world is a rectangle. Any other shape is unacceptable, and I will not tolerate its existence. Okay. So squares are rectangles, but rectangles are not necessarily squares. And so this really comes in from tiling theory. So there's a lot of fun stuff you can do with tilings. People may have seen these patterns on floors and whatnot. If I have a grid like this and I want to try to tile it, it's not that bad to do it by tiling by squares. And if every square is the same size, it's not so bad to just start putting them down and just keep going like this. And then you can ask, what other shapes can you use to tile? And you can do it with an equilateral triangle. You can do it with a square. Can you do it with a pentagon? Can you do it with a hexagon? And you can give students cut out figures to see what can they do. And then you can ask whether or not they can do it with some kind of repeating pattern or a non-repeating pattern. And depending on what you're willing to allow, the answers can become a little bit different. One of the big things I always want to emphasize when I talk to students is the most important part is asking good questions. After a while, you've taken enough classes that you can do the calculations. I say 95% of my job is trained monkey work. You can take anybody who's had similar backgrounds, and once you give them the questions, we know what to do. I could have been prosecuted for notes I wrote when I was in grad school about a certain property. I had no idea it had already been published. I found out years later that it had been published. I had never tried to publish it, and the article was almost identical to what I did. Because once you ask the question, if you have a certain set of training, it's natural to proceed in this direction. So we start off with tiling with squares where they were all the same. We figured that out. That's not too bad. We've all seen that. Equilateral triangles, not so bad. Hexagons, not so bad. Pentagons, that's more interesting. So we could ask about other shapes. What else could we ask? How else could we generalize this question? Yes.
Use two different shapes.
You could use two different shapes. So that's one generalization. What if I give you two different shapes? Do you want to have any constraints on how you can use the shapes?
They have to meet at like vertices.
So one is they have to meet at vertices, no gaps. What other kind of constraints might you have on the two shapes?
They have to have the same side length.
So they probably have to have the same side lengths so they fit in perfectly, good. Or at least some of their side lengths have to be the same. And if we're using regular shapes, then that would be. But there's a lot of, in my mind, I always love to have parameters, dials that I can turn. Do you like to discriminate?
They all need to show up infinitely often.
So that's the lowest bar, is I have to use each one infinitely often. What would a just and equal society say about the two shapes?
Show up as often.
Show up as often. So one possibility is I want to use two shapes, and each shape has to be used in the limit 50% of the time. So as I take a bigger and bigger, circle or square and zoom out, I should be seeing each shape equally often. What if the shapes aren't the same size? What does it mean to be equally often? Does it mean you use the same number of each, or the same percent of the area comes from? So there's lots of questions you can ask. And this is one of the things I try to instill in my students. Ask questions. This is how you generate research. Just get in the habit of asking things and then trying to see what you can do. At the end of the day, most of the questions we ask, we can't answer. And when we write papers, we start off with the question that we can answer. And sadly, they frequently ignore all the other stuff that led to it. Sometimes they're honest and say, we really wanted to answer blah, but boy, was that hard. And then we ended up getting to this special case. So always try to find special cases. So one thing is, if I can use each shape infinitely often, is it possible to do it? Okay, there's another way to generalize this. Any Star Trek fans? Wrath of Khan?
Boy,
That's an old
long
one.
ago.
So in Wrath of Khan,
Is that the one where the bug
yes.
goes with the ear?
And I almost left the theater when that came out.
Okay.
Yes. And so Khan was a brutal dictator, and he was put in suspended hibernation, but then he's thawed out hundreds of years later and causes trouble. And there's a battle between him and the Enterprise. And Spock gives advice to Kirk. He's intelligent, but inexperienced. His pattern indicates two-dimensional thinking. How else could we generalize this problem? Yeah.
Not three-dimensional.
Three dimensions. So what if we try to tile things three-dimensionally? And then this gets you into platonic solids. What kind of objects can you use in 3 dimensions? How much harder is the problem there? And once you do 3 dimensions, what can you do? 4. And then how do we even visualize that? We have tricks to play. And now you can start talking to students. Well, you've all seen projecting 3 dimensions down to 2. How would you try to project 4 dimensions down to 3? Sometimes we do this with color, and there's just lots of wonderful things you can use. Again, a lot of this is meant to be a springboard, to have things for you to think about. You can always tell me, I'd like to do more of that next week. And so right now, I just want to throw a couple things out there. All right. So here's the I Love Rectangles game. And when I do it, I actually bring these very expensive custom-made tiles. And I debated bringing enough for everybody. I just bought enough for me. And so I have tiles of different sizes. And I'm hoping that everybody here has enough mathematical ability that they can visualize these in their heads. If not, welcome to come up. So here's how you play the I Love Rectangle game. We have an unlimited supply of 1x1 squares. We can tile the plane. That's no problem. What if, however, we have exactly one tile that's 1x1, exactly one that's 2x2, exactly one that's 3x3, and so on. So for each n, we only have one n by n tile. Can you tile the whole plane? And here's the rules. When you put the tiles down, you put them down one at a time. You can't put a tile on top of another tile. And at every moment in time, the shape must be a rectangle. So for example, if I just put down this tile, that's a valid start because it's a rectangle. If anybody can put down 2 tiles right now from this, I will give you $40. And when I do this, I actually take out $40 and I take out 40 Canadian. Because I said, hey, look, I never said it was 40 US. And so does anybody think that they can get the $40 from me?
Repeat that again?
Sure. You have to put down tiles one at a time. Can't put a tile on top of another tile. And at every moment in time, it must be a rectangle. And you have exactly 1, 1 by 1, exactly 1, 2 by 2, exactly 1, 3 by 3, and so on. So does anybody think you can put down 2 tiles? Why not?
Because your next one has to be either shorter or longer, and you won't be able to correct it.
That's probably the best phrasing I've ever heard. No matter what you put down. Yes. Because I was going to say, if I put down a 1 by 1, it can't be shorter, but it could be, but you said shorter or longer. And so you're correct. So that is the best phrasing I've ever heard. No matter what you put down, the next tile has to either be shorter or longer. This game sucks. Right? So we need to make this game better. And while Henry has been very generous with the Teachers and Scholars funding, and I will also support with my own funding, funding is still limited. So I am going to do the minimum amount necessary to potentially make this game interesting. I'm going to add 1 more tile. What's the cheapest tile I can add?
1 by 1.
Or 1 by 1. So I think you see where this is going. So I'm going to add 1 1 by 1 tile. Okay. And so now, right. So now we have 2 1 by 1 tiles, a 2 by 2, a 3 by 3, a 4 by 4. Is there any way to put down 2 tiles and have a rectangle? Okay, how can we do it?
2, 1.
The 2 ones. And in fact, when you're talking to the students, you should say, it's got to be something like that, because if I don't use the new 1 by 1 tile, we know that there's no solution. So the first move has to be use that new tile you were given. So we have to put those 2 tiles down. Okay. And so when we do that, we have this beautiful animation, and now we have a 1 by 2 rectangle. Is there anything we can do next?
The 2 by 2.
The 2 by 2. Where should we put it? That's all. Okay. It was a 50-50 chance. What can we do now? 3 by 3, left or right? I just sometimes that. Now what do we put down? 5 by 5. So we never used the 4 by 4. Should we put it up or down? Up. Can we do another one? What can we do next? 8 by 8. And so will we always be able to put down a new tile? Yeah, so that little bit now allows us to cover the plane. Does anybody recognize these numbers? Fibonacci. Yes. All right, so now I can actually take off my jacket. I didn't want to give it away too soon. So I am actually president of the Fibonacci Association and one of the managing editors of the journal. And so if people are interested in, we do have a section on math outreach. And so we love to do things with teachers and students. And so if anybody is interested in trying to get a publication with yourself and your classes, let me know. So we now have the Fibonacci sequence. And so we have a 1 by 1, a 1 by 2, a 2 by 3, a 3 by 3, a 5 by 5, an 8 by 8. And so we have the numbers 1, 1, 2, 3, 5, 8. Do you notice a pattern? So is there anybody here who has not seen the pattern before? All right, so what's the rule to get to the next number from the previous? Add the 2 previous. And so I have done this all the way down to kindergarten, where I provide these to the class. And in kindergarten, they are discovering the Fibonacci spiral. And they're discovering the rules. And so you can keep going and going and going, and you can ask, how do you compute these? And so you don't need to know that much, just basic addition. But if you're trying to get kids to use some good software programs, either Microsoft Excel or Google Sheets, this is a great way to talk to them about writing very simple commands in a spreadsheet to generate more and more numbers. And so there's a lot of wonderful things you can do with the Fibonacci's. So you can do some now basic coding. And then you can start asking, how quickly does the sequence grow? Can you get some upper bounds, some lower bounds? Is it growing very rapidly? Is it growing very slowly? There's a lot of stuff you can do. And so now, here are some interesting fractions. Do you think they're interesting or not? What do you think? I mean, I can write down a tremendous number of fractions, right?
What makes them interesting?
What makes them interesting? So what could you do to try to see if this is an interesting fraction? What might be worth looking at for the fraction? The decimal expansion. And this one I'm not going to do. So the first one is 0.01, 02, 03, 04, 05, 06, 07, 08, 09, 02. The second one is 01, 04, 09, 16, 25, 36, 49, 64, 82, 012. And the last is 01, 01, 02, 03, 05, 08, 13, 21, 34, 55, 90. So what do they look like? Yeah, the first one just looked like the integers, the second one looks like the squares, and the third looks like the Fibonacci's. But the pattern breaks down. Are you surprised that the pattern breaks down? What do you think?
I'm not surprised that the pattern breaks down because it's hard to know what the place value is. So how would you know? Know where the 64 stops being, or like the middle one.
Okay, so in the middle one, it seems like I'm doing things in blocks of 2.
Right, but then you have to change to blocks of 3.
And that's the problem, is then you would have to change to blocks of 3. So if I'm doing some pattern here, what eventually happens is that number, which is 3 digits, the last 2 digits maybe are in its own block, but the previous one gets added to before. So we go from 64 to 96. And so things break down. And so then the question is, can I come up with something that does blocks of 2 followed by blocks of 3 followed by blocks of 4? That's nice. And then, where did these numbers come from? How did I know to look at 100 over 9899? And you give me a sequence and I can find fractions like this. And so again, I'm just, today I'm just trying to put a bunch of stuff out there so that you can then think and tell me as homework which things you found interesting and you want to know more about. Where did these numbers come from? And if I give you a nice sequence, or if you give me a nice sequence, we'll do it that way. Can I come up with a nice fraction whose decimal will be that? And when does it break down? How long will it last? Okay, so this was just a quick introduction. Let me now switch off here. Okay, hopefully this is visible. Okay, yes, excellent. Okay, so there's a lot of stuff you can do with Fibonacci's. I'm going to just double check and make sure things are recording. Whenever you switch, it's always good to just make sure. Nope, okay, it says, well, since it says pause recording, I'm going to, and it has a recording icon, I'm going to assume that means it's recording. So the Fibonacci numbers we're defining as 1, 1, 2, 3, 5, 8, 13, 21, Big Poppy, 55, 89, 1. Well, this is Boston. Okay. And you can even put a 0 in the beginning. So a huge amount of my life is pattern recognition. So we already noticed one big result. Each one seems to be the sum of the previous two. Do you notice any other patterns? Okay, so let's go. So we're going to go even, odd, odd, even, odd, odd, even, odd, odd, even, odd, odd. Is this a proof?
Is this what?
Is this a proof that it's always going to be even, odd, odd? No. Just as an algebra test, can somebody tell me in lowest terms what 16 over 64 is?
1/4.
1/4. Okay, I'm just checking people's algebra. 19 over 95. 1/5. Let's do two more. Let's do 49 over 98. 1/2. Let's do one more. Let's do 12 over 24. 1/2. I'm getting 1/4. Maybe that was decaf coffee.
Wait. What is it, 12 over 24?
Yeah, 12 over 24. That's 1/4, isn't it?
No, it's not here. 'Cause
Let me show my work. All right, 16 over 64, I cancel the 6's and that's 1/4. 19 over 95, I cancel, I mean to cancel that way. I cancel the 9's and that's 1/5. 49 over 98, I cancel the 9's and that's 4/8, which in lowest terms is 1/2. So clearly the way you divide ratios of two-digit numbers where the non-main diagonals are the same is you just cancel. And so 12 over 24, of course, is 1/4.
Nice.
So I like this as this is a really nice example you can give to young kids that just because a pattern holds for a while does not mean the pattern is going to hold indefinitely. This is why we need proofs. And so the Fibonacci numbers, it's starting even, odd, odd, even, odd, odd, even, odd, odd. I think it's going to continue even, odd, odd, but this is not a proof. So let's try to prove it. So imagine we have a block of numbers. So let's do this as a proof. Everybody signed the disclaimer that they are aware that there could be proofs in this class. Yes. It's in a really nice, 2-point font at the bottom. So imagine we have even, odd, odd. Then the next number is even plus odd. It's in red. And what is an even plus an odd? It's always going to be odd. And now we have odd plus odd. And what is odd plus odd going to be? Even. And now, let's do a purple. We're going to have an odd and an odd and an even. What does that become? And now we're going to have, what's a good color? We haven't used orange. Orange is good. Let's do an even and an odd. What's that going to be? And now we see we started with even, odd, odd. Oh, wait a minute. Even plus odd is odd. Oh, wait, I added the wrong ones at the beginning. I circled the wrong things when I wrote things. All right, so we'll quickly redo it. My apologies. Okay, so take two. So we have even, odd, odd. And the first step was we take the two odds, we add them, and that gave us an even, right? Then we take the odd and the even, and that's going to give us an odd. And now we take the even and the odd, and that's going to give us an odd. And now we see that the pattern has repeated. And so we know once we have an even, odd, odd block, it's going to generate another even, odd, odd block. And now this is what I call shampoo mathematics. Has anybody ever heard that phrase? Shampoo, lather, rinse, repeat, right? You just keep doing it. So lather, rinse, repeat. I'm not sure if the repeat is just repeat once or you keep going back. For the computer scientist GNU, if you're familiar with that environment. So this now shows that the pattern will continue indefinitely. Why do we do even, odd, odd? Well, even with young kids, we know about odds and evens. We know about that, split. But instead of doing odds and evens, what could we do?
You mean instead of adding the last two?
Well, no. So let's keep the Fibonacci numbers, because again, as the president of the association, I don't want another sequence to be rivaling us for dominance. Even though the Fibonacci Quarterly will publish stuff on other sequences. Yes. But let's continue to look at the Fibonacci sequences. We just looked to see who's odd and who's even. What could we do instead of looking at odd, even?
Single digit versus double digit.
You could, but we know that the Fibonacci numbers are going to be growing.
Right. Maybe prime and composite numbers?
So you could go all the way to prime and composite. So again, there's no wrong answers. There's just harder problems. So one thing is, we've got 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So one thing we could do is prime versus composite. And that's a really hard problem in terms of, are there infinitely many prime Fibonacci numbers? The Fibonacci numbers turn out to be growing exponentially fast. So just give me one second to just do a quick calculation. I apologize. Okay, so the heuristics do suggest there should be infinitely many prime Fibonacci's, but that's going to be very hard to prove. It's a great question to ask. We do not expect there to be infinitely many square Fibonacci's. I believe there are results on that. And so it comes down to how dense is the sequence. It turns out even though there are fewer primes than composites by a huge amount, there's still a lot of primes. But this is a very different question than even or odd. What's a closer question to even odd?
I was going to the difference between all the numbers.
Okay.
So 1.
Okay, so you want to look at
Sorry,
differences.
I kind of want to skip 0 for my example.
That's fine.
But
So we can skip 0.
that kind of goes against what I was thinking. But
A, E, I, O, U, and sometimes Y. So 0 will be the sometimes Y of the Fibonacci numbers, sure. So we're looking at differences. So we have 0, 1, 1,
2,
2,
3,
3,
5,
5.
7. Oh, sorry, 8.
8.
13.
So what do you notice when you look at the differences? It's the Fibonacci's.
Yeah.
Because Fn plus 1 equals Fn plus Fn minus 1. So if you look at the differences, Fn plus 1 minus Fn is just Fn minus 1. It's just a shifted sequence. So it's a great question to ask, is to look at the differences.
Can you look at just the ones place?
So you could look at the ones place. So another question is, this is called mod 10. So everybody is familiar with modular arithmetic, even if you've never heard that highfalutin phrase. The friendlier way to say this is clock arithmetic. Let's say it's 10 o'clock now. We end in 5 hours. So what's 10 plus 5? 3. So everybody knows 10 plus 5 is 3. Nobody would say 15. Because on a clock, every time you get past 12, you reset and you subtract off as many multiples of 12 as you can. We could do a clock with different number of hours than 12. We could do a clock with 10 hours. And we could look at the Fibonacci numbers and look at just the last 2 digits. And I apologize. So we can now look at the Fibonacci numbers, Fibonacci's mod 10. So if we want to look at the 2 ones, we'd go 1, 1, 2, 3, 5, 8, 13 is 3, 21 is 1, 34 is 4, 55 is 5, 89 is 9, 144 is 4. It's not as clear now. So the question is, do you think that this will eventually repeat? And will it cycle?
Yes.
And can we modify the even, odd, odd proof for this case? So one of the big things to understand in mathematics is sometimes you can roll up your sleeves and do a really painful calculation. And then if somebody changes the problem, you have to roll up your sleeves and do another painful calculation. Or you can try to find a way to do all the calculations at once, try to generalize and abstract. So for a lot of the proofs, we can just roll up our sleeves and just do the damn calculation straight out. Or we can try to find a way to do them all at once. Rather than doing mod 10, we could view as what we did initially as mod 2. I do even or odd. What might be easier than mod 10? Mod 3. So, again, it's not clear what's the next question to ask. From even odd, is the next question to ask, let's look at the tens digit? Or is it to say, let's look and see, does it repeat when we look at the remainder when we divide by 3? So if we do now mod 3, we would get 1, 1, 2, 0. And then let me just write the Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, dot, dot, dot. So we just did 3. So what would 5 be when we look at the remainder of 5 divided by, would be 2. The remainder of 8
3. No, 2.
would be 2.
Sorry.
Oh, so we just did 8, which was 2, sorry, 13.
3. No, sorry, 1.
1,
I'm
1.
looking at mine.
Yep. 21 is 0. 34, 1. I don't know why I changed to blue, but 55. Everybody agrees at 1?
Yeah.
54, okay, 1. And what's 89? 2. 144, 0. So do we notice a pattern?
Did you keep going?
We could keep going. So what comes after 144? 233? And what would be the remainder of 233? It'd be 2, I believe. Because 231 is a multiple of 3. So it's 2 more than that. We can talk about those tricks in a moment. After 233 becomes 377. So 370,
So 1.
so that would be 1. And so notice the pattern seems to be going on. So it seems like our repeating block is 11202110. And so we, if we put a 0 in the beginning, we would have started a little bit earlier. So maybe we will put the 0 back to just start off like this. So this looks like it's our repeating block. And then we have another copy of that block. Yes.
Can you explain that again, how you're getting the numbers?
Sure. So what I'm doing is I'm looking at the remainder of the numbers when I divide by 3. So 8 is 2 times 3 plus 2. So its remainder when I divide by 3 is 2. 13 is 4 times 3, which is 12, plus 1. So its remainder is 1.
Oh, so it's the remainder.
It's the remainder. 21 is 7 times 3 plus 0. So I'm looking at the remainder when I divide by 3.
Oh, okay.
And so when we do odd even, we don't really have to do the division. We're all comfortable enough with, is the number even or odd that we don't have to write all this out.
Why does it, why did you say 3? Why?
So 3 was the next number after 2.
Okay.
And so-
Say the 3 and fraud one time, and it just really stuck with me.
Oh, nice. I mean, I like using thrice, so I'll have to remember thought.
Because generally speaking, mod 2, like you said, mod 2 kind of goes without saying, so mod 3 is the next.
Right, and so we have language for mod 2. We have even odd. We don't really have as good language for 3. Or as good. Now for 10 is a natural thing to do because it's just looking at the last digit. And so here Do you think once we have a repeating block, that block is just going to self-propagate? Could something strange happen?
Wouldn't the answer be no, because you're going off of the original pattern of it being even, odd, odd?
Right.
So wouldn't this pattern, let me rephrase this.
Yes.
Could that pattern can't be interrupted as long as the odd, even pattern doesn't get interrupted, which it won't?
Well, but this is now different than the odd even, because now we're looking at things with threes. You're on the right track. I mean, what we did
Oh, I see.
before is each number came from adding the two previous. So over here, I took the 0 and the 1 and I added them. And I took the remainder and that gave me the 1 over here. And so the question is this going to force the same pattern to keep repeating? So for instance, over here, I know I have this 2 and this 1 are going to combine and give me the 0. So does that mean this 2 and the 1 over here is going to combine and give me the same number there? It's going to be the same, right?
You have to reset.
You have to reset. And now this 0 and the 1 giving me the 1, I'm sorry, I now need 1 and 0. And so if I now take the 1 and the 0 over here, these two will combine and give me the 1 here. So then the 1 and the 0 here will combine and give me a 1 over here. And so the pattern will push down.
Does that work for all mods?
So it will work for all mods. So the question is, what level of rigor do you need? For little kids, and we can argue exactly what the definition of a little kid is, I think this is more than enough rigor. For Math Journal, this is not enough rigor. And it's important to know, what is your audience, what is the right level, to just see it's going to keep propagating. And so it turns out you give me any number, and I look at the Fibonacci's mod that number, and it will always repeat. And we have some understanding of how long it takes before things repeat. Has anybody here heard of either the pigeonhole principle, the box principle, or Dirichlet's box principle?
Is it the pigeonhole with the birthday paradox?
No, the birthday paradox is something else. So the pigeonhole principle is one of my favorite things in all of mathematics. Imagine you have n plus 1 pigeons, and you have n boxes, and you have a pigeon gun, and you load the pigeon gun with pigeons, and you shoot the pigeons into boxes. So this is box 1, this is box 2, this is box n. So you have n boxes, and each pigeon has to go into one and only one box. At least one box must have what happening? Yes, so must be at least one box with 2 pigeons. And if that weren't the case, then each box would have at most 1 pigeon, and that would only account for n pigeons. So this is the pigeonhole or the box. Sometimes they put Dirichlet's name next to it, principle. It is amazing how powerful this is. So another way of looking at it is impossible for every box to be below average. The average number of pigeons per box is greater than 1. If every box had less than the average, how could you get up to the average? This is similar to if you're driving in your car and you've traveled a certain distance in a certain time, and you know what the speed limit is. If you've done that too quickly, we know there must be at least one moment when you were speeding. So intuitively, this is not a hard concept to grasp, the pigeonhole principle. It's just saying everybody can't be below average, right? At least somebody must be average. And because we're dealing with integers, you can't have 1 1/4 pigeons. You have to be at least then 2 pigeons here. So how does this help? And again, you all heard Henry warn you that you do not have to understand every moment of every part of today. I will just give the high level proof. Given any modulus M, the Fibonacci's mod M repeat in at most, let's say maybe M squared plus 1 steps. So no matter what modulus you give me, you can give me 2, 3, 10, 1776, 2004. Eventually the Fibonacci's will repeat, and I know how long I have to wait. It's no more than this. And here's the proof. We have adjacent Fibonacci numbers mod M. How many possibilities are there here? So how many remainders can there be mod M? So mod 2, how many possibilities were there? 2. Mod 3, how many possibilities were there? 3. Mod 10, how many possibilities were there? So there's M possibilities here. How many possibilities are there here? Is how many? For that box, it's the same. It's also M. So we only have M squared possible pairs, mod M. So if we look at say box 1, box 2, box 3, box M squared minus 1, M squared plus 1, I claim we have to have the same pair observed multiple times. Because if all the pairs were different, how many pairs do I have from here to here? Do I have to go up to M squared plus 2? Let me go up to M squared plus 2 just to be safe. So this is my first pair. This is my second pair. And then this will be my M squared minus first pair. This will be my M squared pair. This will be my M squared plus 1 pair. I can't have all those pairs be distinct. I have to see the same pair twice. Everybody agree with that? So the pairs are my boxes. We only have M squared options. But over here, I have M squared plus 1 pairs. So the adjacent numbers give M squared plus 1 pigeons going into M squared boxes. So in the pigeonhole problems, you always have to figure out what's the pigeon, what's the box. And so looking at what's going on, I have too many pairs for them all to be distinct. So if I look at things, mod 10, I only have 100 possibilities. Well, if I look at 101 options, they can't all be distinct. So what does that mean? It means at some point, I have to have over here, and maybe I'll call this alpha and beta, and I'll have alpha and beta again. So they have to be the same. And once I have alpha and beta here, they're going to give me a new number here, and then these will give the same new number. And so once I have a repeat, I'm going to just march along and keep repeating. So this is a rough outline of how you can show that the Fibonacci's will repeat no matter what. Then it becomes a more interesting question, how do you determine what the period is? This is an upper bound. Is it really that bad, or is it much smaller? Does it depend on the factorization of the number? There's lots of questions you can ask. We'll end with one more thing, and then we'll have our first break, because it is much easier to be the teacher than to be the student. Yes.
Can I ask you a question then? Doesn't it start messing up if you get to mod 11 or something? Because then you have a 2-digit remainder, right?
But we're no longer looking at it mod 10. We're now looking at mod 11. So if I just looked at 12 consecutive pairs,
Right.
at least 2 of those 12 consecutive pairs would have to be the same mod 11. I'm not looking at just the last digit.
But isn't it like the fractions that turned into a decimal that eventually you're gonna? Oh, right, because you're thinking of it as never mind.
Oh, I'm thinking it as an ordered pair.
Right, I get it.
And so the ordered pairs would have to be. So I will just end with one last question. I'll skip the 0 and I'll only include 1, 1. 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, dot, dot, dot. Okay. So when I went to the elementary school, the kids noticed the odd, even pattern, or it's a little bit different here because I killed the 0 and the 1 at the beginning. I gave this to some of my college students, and I asked them what patterns do they notice. And again, we went much further than 144 because these were college students. And one of them made a very interesting observation that every Fibonacci number has a digit of either 1, 2, 3, 5, or 8. Was not expecting that. Was expecting even, odd, or something like that. Why do you think you have to say every Fibonacci number has a digit of 1, 2, 3, 5, 8? Do you think you could do a smaller set? Okay, so why can't we do a smaller set?
Just within the first 5.
Yeah, just within the first 5. So what you could do is, mathematicians sometimes like to say, well, there's a couple of exceptions in the beginning. So you could say all sufficiently large Fibonacci numbers have 1 as a digit. That's an open problem. I would be shocked if your number was sufficiently large if it didn't have a 1. So my students and I were able to prove some results along these lines. We have some weak results about what can and cannot happen. But the goal is you never know where things are going to go when you ask questions. And sometimes it's little kids who ask questions. I may talk in the next day about a game inspired by my son, which led to multiple research papers. And so the goal is just always be inquisitive. What I hope you got out of this first springboard thing is, hopefully you've seen the Fibonacci numbers before. There's lots of ways you can go with this depending on what skills your kids have. It can be anything from just tiling and then introducing them to all sorts of tiling problems and shape problems, trying to come up with good questions. It's okay if they can't solve them. In fact, it's even better for them to see that this is ongoing. We don't have all the answers in math. That's why it's good to know professors. When I was a younger professor at Williams one day, a physicist came to me with one of his students, and they needed some results on exponential sums. I'm just going to be a little bit careful how I face this because this is being recorded. And I was able to prove a few things, but exponential sums is not my main area of research. And for what you really need, you need an expert in the subject. I happen to be really good friends with somebody who wrote one of the classic books in the field. If you want, I can pass on your question, please. So I write to my friend Ron, goes, oh, no, this is beyond me. You need Nick Katz for this. Would you like me to talk to him? I mean, I knew Nick Katz, but Ron knew him better, so please. So he talks to Nick, and Nick writes a 50-page paper titled On a Question of Roots, who was the physicist. This is how research works. Can you find a way to interest the people who have the skill sets to attack the problem? And the big contribution from Wooders and us was to come up with a question that had real interest, enough that one of the top mathematicians in the world was willing to devote a tremendous amount of time trying to resolve it. Good questions come from so many places. if I ever become royalty and I get to have a shield and a crest, I will have a hammer on it. Does anybody know the law of the hammer? Nobody knows the law of the hammer? The law of the hammer is if all you have is a hammer, pretty soon every problem looks like a nail. There's a lot of ways to look at this. I do not want to talk political positions. Has anybody ever watched a presidential debate or anything like that? I think it's safe to say that no matter what question is asked, the candidate has something that they want to say. And their goal is to migrate to what they want to say. And the good ones can do it smoothly. If all you have is a hammer, you try to convert whatever you're given to what you're good at, so you can hit it with your hammer. That's one way to look at the law of the hammer. But I tell my students that's only half the story. The other half is go to the land of the screwdriver. They're not idiots. They just have a different skill set. And if you can look at problems in a different way, you have the ability to make a real contribution. Do not go against Gauss in elementary number theory. He will beat you, even though he's dead. Right? Good people have been studying these problems for a long time. It's hard. I do have some friends who have found things that were missed. It's very hard to do. But if you are trained in one area and can talk to people with different skill sets, you have the opportunity of tremendous achievement. And so I have written papers in a huge variety of subjects. When my wife and I were dating in grad school, I was at Princeton, she was at UPenn. Some of her professors were like, wait, you're dating a mathematician? Can we talk to him? And so I started writing papers with marketing professors. And I was able to put in number theory and combinatorics in places they normally wouldn't have thought to do it because I had a different skill set. So in terms of trying to motivate students, you want to find a little bit of everything. This is one of the advantages of being at a liberal arts college. You learn a little bit of everything. And then you know, who do you talk to? What skill sets are out there? What things are possible? And so over here, this was a problem that I would not have thought of. My mindset was, oh, it's the odd, even, stuff like that. But it led to some really interesting questions. And the goal is, as much as possible, to try to encourage your students and teachers to just be creative, explore, to have fun with the material, and just see where it goes. And if you get stuck, call a professional, right? We don't charge. We love it when people come up to us. My second paper was, no, I think I'll stop here because it's 10:45, and I don't want to go too far without taking a break. So let me stop recording.
Was there a group that ever thought about why Fibonacci